So what we've seen so far is that sometimes we can have multiple correct but equivalent Lewis structures. Occasionally we'll find that we'll be able to draw multiple correct but non-equivalent Lewis structures. When that's the case, we'll use the concept of what we call formal charges to decide which of those non-equivalent Lewis structures is the best one and probably the best approximation of what the actual molecule looks like. So we're going to illustrate this by working through the example of nitrous oxide. So nitrous oxide is commonly known as laughing gas, and it's often also used for whipping cream, and it's sometimes used as an anesthetic. So a guy called Sir Humphrey Davy, he popularized the recreational use of laughing gas in the 18th century, and people would come to these parties and they would pay money for it, and he would, squirt laughing gas into their mouth with a big set of bellows, and so he would synthesize it on the spot, and that's what all of this, this is a piece of equipment called a retort that he's using to synthesize the N2O, and then people would get their buzz and everyone would kind of like roll around having fun. And people still do this to this day. People inhale whipped cream canisters for this purpose. Now there was a guy that attended one of his parties, and he actually ended up he observed that sometimes the people who were inhaling laughing gas seemed to be sort of like they didn't experience pain. And so he kind of then investigated the use of laughing gas as an anesthetic, and he made all the money, right? So that's where all the money is. So the take-home message here is don't be a drug dealer, be a pharmacist or a medicinal chemist. So we're going to draw the Lewis structure for N2O. So nitrogen's in group 5A, and we've got 2 of those guys, and oxygen is in group 6A, so we've got 6 of those guys, and so that gives us 6 electrons there. Nitrogen's going to be our central atom because it's in group 5, whereas oxygen is in group 6. So the general layout is going to look like this: nitrogen, nitrogen, oxygen. So we need 2 single bonds to join everything together preliminarily, so that's going to use up 4 of our 16 electrons. So now we're going to complete the octet on our outer atoms by putting 3 lone pairs on each of them, and then that uses up the remaining 12 electrons. So step 5 isn't needed because we don't have any electrons to place on our central atom, and now we just have to have a look at our central atom and see what we have to do to get it to have an octet. So we see that there are 4 electrons around our central atom, so we need to bring in another 4 electrons. The question is, how do we do it? Do we bring in 2 here and 2 here? Or do we bring in 4 from here? Or do we bring in 4 from here? Or does it make any difference? Now, I might think, that nitrogen has 3 octet vacancies and it likes to form 3 bonds, and oxygen has 2 octet vacancies and likes to form 2 bonds. Is there a way of doing that? Would that be the best Lewis structure? Is it impossible to achieve that? So how am I going to figure this out? So, complete the octet on the central atom by forming multiple bonds. One way of doing it would be to bring in, just like we did with carbon dioxide, 1 from each side, and to have this nice symmetric structure. But you can see here that the nitrogen on the end here has 2 bonds. The nitrogen in the middle has 4 bonds, and only the oxygen on the end gets what it wants with 2 bonds. So maybe there's a better way of doing it. The other thing that we could do is we could bring all 4 of the electrons in from the oxygen end. But then this guy would have 1 bond, this guy would have 4 bonds, and this guy would have 3 bonds and none of them would be happy, right? Because nitrogens all want 3 bonds and the oxygen wants 2 bonds. So the third way of doing it would be to bring in all 4 electrons from the nitrogen end of the molecule. So we would end up with this structure where we have a triple bond between the 2 nitrogens. And then this guy is happy because he's got 3 bonds. This guy's unhappy, he's got 4 bonds. And this guy is unhappy because he wants 2 bonds, but he's only got the 1 bond. So there really doesn't seem to be a way that we can draw a Lewis structure that kind of aligns with what we would expect to be the number of bonds formed. There's going to have to be a compromise. So, in this scenario, there are 3 possible resonant forms and they're not equivalent. So how do we decide what is the most important? And this is where the concept of formal charge arises. So we're going to use the concept of formal charge to decide what resonant form is the most important when we have multiple non-equivalent but correct Lewis structures. So the formal charge of an atom in a molecule is the charge the atom would have assuming perfect covalent bonding. That is, that the electrons were being shared exactly equally. And you can calculate it using this formula here. It says that the formal charge is the number of valence electrons on the atom minus the number of non-bonding electrons plus the number of bonding electrons on 2. But keep in mind that your number of valence electrons is just your group number. Your number of bonding electrons is just, the number of electrons that are non-bonding. And then your bonding electrons on 2, that's just equal to the number of bonds. Because remember, every 1 bond equals 2 electrons. If I have 2 bonds, 4 electrons. If I have 3 bonds, 6 electrons. So the number of bonding electrons on 2 is just the same as the number of bonds. So your formal charge is just your group number minus your non-bonding electrons minus your number of bonds. We'll go through this slightly. The best Lewis structure will have formal charges as close as possible to 0 for all atoms. So a great Lewis structure will have 0 for all formal charges. If that's not the case, the best Lewis structure will always have the most negative formal charge on the most electronegative element. So we've got nitrogen, oxygen, fluorine. We would want the most electronegative element here is fluorine. We would want, if these 3 atoms were in a compound, we would want this guy to have the most negative formal charge, and perhaps these guys have more positive ones. Okay, so we've got these 3 Lewis structures here. We're going to assign formal charges to every atom in all 3 of them. So ultimately, we're going to assign 9 formal charges. So I'm just going to work at this atom here. So the one on the end, this one. So it's group number minus bonds minus non-bonding electrons. So it is 5 minus 1, 2, 3, 4, 5. So that gives me 0. Right? Group number minus bonds minus non-bonding electrons. The next one, the group number for nitrogen, still 5. 5 minus 1, 2, 3, 4. 5 minus 4 plus 1. No non-bonding electrons in that case. Now I'm going to do the oxygen. The group number becomes 6 now. 6 valence electrons. 6 minus 1, 2, 3, 4, 5, 6 non-bonding electrons minus 1 bond. So 6 minus 7 gives me a formal charge minus 1. Okay. So you can kind of go through it, but just keep in mind you can see pretty clearly here that your bonding electrons, right, your bonding electrons divided by 2 is just equal to your number of bonds that's in your structure, your number of lines that's in your molecule. All right, let's move on to the next one. Now we've got that. This guy on the end, the nitrogen, so it's going to be 5 for the valence electrons, 1 for the bonding electrons on 2 because there's one bond there, and then finally 1, 2, 3, 4, 5, 6 minus 6 for the non-bonding electrons. So 5 minus 1 minus 6 gives me a total of minus 2. Moving on to the next nitrogen, it's 5 because that's its group number. Then we're going to do the non-bonding electrons on 2, so that's the number of bonds. 1, 2, 3, 4, 5 minus 4. And then there are no non-bonding electrons there, so 5 minus 4 gives me plus 1. And then finally the oxygen, so the valence electrons is just the group number minus the bonding electrons on 2, so that's 1, 2, 3. 3 bonds there, minus my non-bonding electrons, minus 1, 2. So 6 minus 3 minus 2 gives me plus 1. Okay, so we've got the second Lewis structure assigned with formal charges. Now I move on to the third one. Nitrogen on the end there, 5 minus 1, 2 bonds. So bonding electrons on 2 is going to be 2 minus 1, 2, 3, 4 bonding electrons. 5 minus 6 gives me minus 1. Okay, and then finally, or not finally, the next nitrogen, 5 for the group number for the valence electrons. 1, 2, 3, 4 bonds. So bonding electrons on 2 is 4 and no non-bonding electrons. So 5 minus 4 is plus 1. Then the oxygen, 6 minus 1, 2. Bonding electrons on 2, and then minus the non-bonding electrons 1, 2, 3, 4, and so that gives me 0. All right, so what were our 2 rules? They were formal charges should be closest to 0. So we can get rid of this one because it doesn't have any that are near 0. It has this thing here with this big minus 2, so that's going to be a bad one. And then our next rule was that the most electronegative has to have the most negative formal charge. So we've got 2 atoms here, nitrogen and oxygen. And oxygen is the most electronegative element of that pair because it's right next to fluorine. So the good formal charges will have the most negative one on the oxygen. So this guy has the most negative formal charge on the nitrogen. That's no good. And then this one, yep, it has the most negative formal charge on the oxygen. So there we go. All right, so it's going to be that one with the triple bond between the 2 nitrogen atoms and the oxygen attached via a single bond. So both A and B have formal charges closest to 0. However, only the first structure has the most negative formal charge on the most electronegative atom. So we're going to say that this one is most likely closest to the true structure of N2O. So general rules of thumb are, when an atom meets its bonding capacity, it'll have 0 for its formal charge. So if you look at this nitrogen here, it's forming 3 bonds, and sure enough, its formal charge is 0. And if you look at this oxygen atom over here, it's forming 2 bonds, and sure enough, its formal charge is equal to 0. So our rule about formal charges being closest as possible to 0 is really saying that atoms should, it's preferred when atoms meet their bonding capacity. Now, every time you go over the bonding capacity by 1, the formal charge goes up by 1. So you can see that here, this nitrogen atom in the middle here has 4 bonds. It's gone over its bonding capacity by 1, and sure enough, it's plus 1. If you look at this oxygen atom here, oxygen likes to form 2 bonds, but this guy is forming 3. It's gone over its bonding capacity by 1, and sure enough, its formal charge is +1. Similarly over here, nitrogen likes to form 3 bonds, but this one in the middle here is actually forming 1, 2, 3, 4. It's gone over its bonding capacity by 1, and sure enough, its formal charge is +1. Now, when you go under the bonding capacity, you go -1 for every bond less than the bonding capacity. So let's have a look at some examples here. This oxygen atom, oxygen likes to form 2 bonds. This guy is only forming 1 bond. It's 1 under, formal charge -1. This nitrogen atom on the end here, nitrogen likes to form 3 bonds, but this guy is only forming the 1. It's 2 under, formal charge -2. This nitrogen here, nitrogen likes to form 3 bonds, but this guy is only forming 2. It's 1 under, -1. So that's kind of how it all works. These are sort of general descriptions of how you can kind of quickly tell whether an atom is meeting its bonding capacity or not, and also quickly tell what the formal charge is likely to be. Now, something else to note is these guys are all molecules, so the sum of your formal charges always equals the charge on species. So as these are molecules, they all have a 0 charge, and your formal charges all add up to 0 in each case. If you have a polyatomic ion, say you had sulfate, then the formal charges, when you add them together, will equal the charge on your polyatomic ion. So we already kind of know the answer to this one because we drew it correctly right from the beginning, but this question is asking use formal charges to decide which of these resonance forms best describes the bonding in carbon dioxide. So we've got one here with 3 bonds to this oxygen and only 1 bond to that one. So let's do the formal charges. It's going to be 6 because oxygen is in group 6, minus the bonding electrons on 2, 1, 2, 3, minus non-bonding electrons, -2. So that's going to be +1. Carbon is in group 4. We've got to subtract away 1, 2, 3, 4 for the bonding electrons on 2. No lone pairs, so that gives formal charge of 0. And then we've got this final oxygen on the end, 6. It's making 1 bond, and then 1, 2, 3, 4, 5, 6 non-bonding electrons. And so that gives me -1. Now I go through and I do that for all of my guys that I've got there. And I'm just going to hurry along. That will end up being 0. That will end up being 0. That will end up being 0. And then we'll look at this one. 6 minus 1, 2, 3, 4, 5, 6, 7. So that's going to be -1. 4 minus 1, 2, 3, 4. So that will be 0. 6 minus 1, 2, 3, 4, 5. And that will be +1. Okay. So you can see what I was doing there. I'm doing just like group number minus lines and dots, right? That's what I'm doing. And that equals your formal charge. So you can do it very quickly. You don't need to do all of these elaborate things here. Okay, so what one's the best one? Well, it's that one in the middle there, isn't it? All right, because it's got all the formal charges closest to 0. So that's it. And the other ones don't really make sense because you've got the most electronegative atom here is oxygen, and so it should always have the most negative formal charge, which it doesn't in either of those. So they don't make sense at all. Okay, so that concludes the section on formal charges. There will be another video where we look at octet rules, and the reason for putting it here is because we're going to use the concept of resonance and formal charges to explain some of these octet rule exceptions.